So, just want to make sure that this is all working. Give me 2 seconds. Brilliant. Nice. Right, guys, so we're going to go through a full paper 2 today. This is the 2021 paper. It's higher tier. I thought that would suit most people. The foundation paper will still take up pretty much half of this. So the second half of the foundation paper will be the first half of the higher tier paper. And this will also be useful for triple as well, because triple, the content really doesn't change that much from higher tier. It's just a little bit of nuance, so a little bit of additional information that you have to do at higher tier. At triple. So it should be useful for everybody, this. We're going to go through it step by step. If there's any questions you want to ask as we go, just please put them in the comments and I'll answer them live for you. Right. So I'll read through the question. Question number 1 says, a student investigated the reaction between magnesium and excess hydrochloric acid. In this method, it says they pour 50 centimeters cubed of hydrochloric acid into a conical flask. Then they add a piece of magnesium. They insert the stopper and the delivery tube and start the timer. Collect the gas in the gas syringe. They record the volume of gas produced every 20 seconds for 2 minutes. And then they repeat it with a different or higher concentration of hydrochloric acid. So the first question on this paper is, what is the independent and control variable? Well, if you don't know your variables, what's really good is if you remember, don't mess in class. So I'll just write that down. I'll show you what that means. Don't mess in class. So the first letter of each word is like an acronym for the variables. Dependent is something you measure, and an independent is something you change. So our independent variable is something we change. So what is changing in this experiment? If you ever are stuck with something like this, look for the word repeat, because after that it will usually tell you what they're going to change. So it says repeat steps 1 to 5 with higher concentrations. They are changing the concentration of hydrochloric acid. And now the control is whatever you're keeping the same. So I would always say, look for the other reagent on this. So if they're changing the acid, you want to keep the magnesium the same. And specifically, you want to keep either the mass or the size of the magnesium the same. So that, fairly straightforward question to start off with. That shouldn't be too challenging. Let's have a look at this second one. Right, on this one we've got to do a graph. So it says table 1 shows the results from the experiment using hydrochloric acid with a low concentration. You should plot the data in table 1, note that the point 00 has been plotted for you, and draw a line of best fit. Now in graphs, you have to plot them accurately. You can't just put them in a rough area where you think that that's where the value should go. So we're going to go through this. 00 has been done for us. So we've got to do time 20, volume 48. So time 20, and we've got to go 40. 50 is halfway between 60 and 40, and 48 will be here. Now it's going to be hard to do with this tablet here, but I'll do my best. So then 40 seconds, and the volume of gas was 72. So 70, there you go. So each little square is 2. 60 is 90. That's an easy one because it's halfway between 80 and 100. 80 is 97. So 92, 4, 6, so 7. And then 100 is 98. And then it's also 98 for 120. Now here's basically what I would say for a line of best fit. If you see that the last 2 numbers, or even last 3, are either the same or start to curve off, start to tail off, then I would always do a curved line of best fit. If the numbers are increasing in a linear order, by that I mean like doubling, then you would do a straight line of best fit. So because this is curved and it's got two numbers at the end, it goes flat, do a curved line. And the best thing to do, and this is going to be extremely hard here, is you do a smooth line through as many points as possible. That turned out better than I thought it was going to do. But obviously I missed these three here. You'd want to go through those with your pencil. So that creates a nice line of best fit. Let's have a look at the second one, or the third question on this one. How does the rate change with time? Well, for this, you look at the steepness of the curve. So at the start, we've got quite a steep line. So the rate here is increasing at the start. Then about midway, so throughout the reaction, it starts to slow down. And eventually, you see here, it gets a horizontal line because the reaction has stopped. So over time, the rate of reaction decreases. You might like to think that actually it increases, it gets faster over time. It does at the start, but then over time it actually goes down until it stops completely. The student repeated the experiment using hydrochloric acid with a higher concentration. What statement is correct? So if you increase the concentration, you're increasing the number of acid particles, if you like, that are available for reaction. So if you've got more particles to react with, you're going to get a faster reaction. So let's look for something that talks about the reaction getting faster. So the activation energy for the reactivation was higher. Well, that's not going to be correct because a concentration wouldn't affect activation energy. The magnesium would react more quickly. Now, straight away, I'm thinking it's going to be that one. But let's have a look at the other two just to be certain. The reaction finished at the same time. Well, if you increase the concentration, you might find that the reaction particularly would maybe end at the same time if they've got the same number of particles, so you're going to have a limiting reagent. But that's not going to be the best thing there. Then the total volume of gas collected was smaller. Well, actually, it's probably, like you say about the limiting reagent, it will probably be the same volume, you just get there faster. So the answer here is about the rate increasing, it's getting quicker. Next question. Temperature also affects rate of reaction. It does. Explain how increasing the temperature affects the rate of reaction. You should refer to particles and collisions. Now, we have to talk about particles and collisions. It's told us that. And I've been doing a lot of this in my lessons at the moment because this is something students really struggle with. Collision theory, talking about why or what happens when particles collide. So we need to talk about how temperature affects rate. Well, if you increase the temperature, particles gain more kinetic energy. They move more. Particles gain more kinetic energy. If they get more kinetic energy, they're going to move more. So they're going to collide more. They're going to hit each other more frequently. And if they hit each other more frequently, there's going to be a higher chance or a greater chance that those collisions will be successful. So the rate of reaction will increase. So you get more energy, so they move more. You get more frequent collisions because they're moving around with more energy. And the energy that they collide with is more likely to be equal to or above activation energy. So the successful collisions will occur and you'll get a higher rate. Moving on to question 2 now. So there's 6 questions in this paper, I believe. So we're moving okay. Crude oil is a resource found in rocks. Most of the compounds in crude oil are hydrocarbons. Complete the sentence. Crude oil is formed by the decomposition of, my favorite chemistry question because I absolutely love the answer, which is plankton. So plankton, just like from SpongeBob, they break down, they decompose, and they will eventually, over millions of years, form crude oil. Now, alkanes are hydrocarbons. Give the name of the alkane molecule that has 3 carbon atoms. Now, the first the first sort of alkane with 1 carbon is called methane. The second is called, hopefully you know, ethane. Then the third, propane. And the fourth, butane. Now you only need to know the first 4. This one asks what's the one with 3 carbons. So it's the third one down, propane. Six marker now. Well, when you see a 6 marker, do not get put off just by the fact that there's a lot of information and there's 6 marks and a lot of lines. Just try and add something. You'd be surprised at how many marks you can pick up by just bullet pointing some very simple statements. So this one says, figure 3 shows 2 alkane molecules, methane and hexane. Table 2 shows the melting and boiling points of methane and hexane. Compare the structure and properties of methane and hexane. So we have to compare what they're like, both in terms of structure, so how they're put together, and properties, so what they're like. So let's have a look at the structure first. So if you look at methane, the structure of methane is that it's got 1 carbon and 4 hydrogens, all connected by single bonds. Hexane has got 6 carbons and 14, so 6, if you remember the general formula for an alkane, it's the number of carbons doubled plus 2. So 6 times 2 is 12, plus 2 is 14. So it's got 14 hydrogens, again, all connected by single bonds. So let's compare the properties. So what's similar about them? Well, methane and hexane are both made of carbon and hydrogen only. Both have single bonds as well. Both of them, there's no double bonds there, is there? Both are actually relatively small molecules. You might think that 6 carbons is quite big, but actually in the world of chemistry, 6 carbons and 14 hydrogens isn't that big. So they're both small molecules. Let's have a look at what's different about them. Well, carbon in methane is only 1, but the number of carbons in hexane is 6. So that's a difference. So there's 1 times carbon in methane and 6 times carbon in hexane. Now, if we look at the number of hydrogens, that's also a mark. There's 4 hydrogens in methane and 14 in hexane. Now we've just talked about the structure there, and we've got quite a lot of marks already. But now we need to move on to the properties, and this is going to be the properties here, the melting and boiling point. So both methane actually have very low melting and boiling points. So you can see methane has a melting point of minus 183, hexane minus 95. Boiling point of methane is minus 162, and the boiling point of hexane is 69. Now 69 is still pretty low in terms of boiling point. So they both have low melting and boiling points. They're both flammable as well, actually. But what's different about them is that methane has a lower melting and boiling point than hexane. So let's write that up. Both flammable, have low melting and boiling points. Now, methane has a lower melting and boiling point than hexane. Methane's melting and boiling point is lower than hexane. Now, there's lots of other marks you could get from this question. So if I haven't touched on yours, that's absolutely fine. I've linked in the description a link to the mark scheme. So have a look. I'm sure your answer will be covered in there as well. But these are just the ones that I came up with to get 6 marks. Now for 2.4, it says hydrocarbons are cracked to produce more useful alkanes and alkenes. Decane C10H22 is cracked to produce 2 products. Complete the equation for the reaction. Now, when you see cracking equations, the left side has to add up to the right side. Conservation of mass. If I have 10 carbons at the start, I have to have 10 carbons at the end. Now, I've used 2 of them to make ethene here. So how many carbons do I have left? I have 8. 8 plus 2 is 10. So that makes it equal to the left. Let's have a look at the number of hydrogens that I would have. 22 on the left, 4 used on my right, so 18 there. So C8H18 is my missing molecule. Question 2.5 says C2H4 is an alkene. What is the test for alkenes? Give the result of the test if an alkene is present. Well, this is more of a memory task. There's nothing clever here. There's no way to work it out other than just knowing that the test is bromine water. If I add bromine water to an alkane and an alkene, well, what happens if I have an alkene present is that the bromine water decolorizes. It goes from orange to colorless. Will change from orange to clear and colorless. Now, what I want to draw your attention to is whenever you're doing a change, so for example, a color change or even an observation, you want to say what it was like at the beginning and then talk about what it was like at the end. So the color was orange to begin with, then it went clear and colorless. Always give the before and after. Question 3. The methods used to produce potable water depend upon the available sources of water. Suggest how copper sulfate can be used to test for the presence of water. Well, this is a very tricky question actually, probably the hardest question that we've come to so far. It relies on you knowing about hydrated and anhydrous copper sulfate. So if I add water to copper sulfate, if it doesn't have any already, we call that anhydrous, without water. If I add water to it, then a colour change happens. It turns blue. Copper sulfate without water is white. So how could I test for the presence of water? I would take anhydrous copper sulfate and that can be added, and if the water is present, it will turn blue. Okay, so if there's water present, the copper sulfate will turn blue. It's white to begin with, then it'll turn blue. The boiling point is used to check the purity of a sample of water. In chemistry, what is meant by a pure substance? So in chemistry, it's slightly different to everyday life because you might see, pure spring water, for example, advertised in shops in bottled water. But pure in chemistry means it's only one element or compound. Pure spring water in the shop might have lots of other substances in there. But we say in chemistry that pure means one element or compound. So it's only made of one element or one compound. Right. The boiling point of 250 gram sample of water was 100.60 degrees C, and the boiling point of pure water in the data book was 100 degrees C, what you'd expect. Each 1% of impurity increases the boiling point of water by 0.12 degrees. Calculate the mass of impurity in the water sample. Right, for this one, we need to know, basically, how many times has the impurity affected the degree C. So I can probably explain this a little bit better if I show you here. So the boiling point here of the sample is 0.60. That's how much higher than the original or the data value is. Now, for every 0.12 of increase, that's a 1% impurity. So I need to find out how many times it's increased by. What percentage is it increased by? So I'm going to see how many times 0.12 goes into 0.6. And that'll tell me how many 1% effectively, how many percentage of impurity there is. So 0.6 divided by 0.12, that's 5%. Okay? So there is a 5% impurity of this. So in 250 gram sample, 5% of it is impure. Now we need to know what 5% of 250 is. Now the best way to do that, personally, I would find 10% and half it. So we know that 10% is 25 grams. Half of 10% is 5%. So half of 25 is 12.5. So 12.5 grams of that substance is impure. 12.5 grams is what led to the impurity and the change in the boiling point. Explain how distillation is used to obtain potable water from salty water. Distillation is a process whereby we boil the water. We heat it up. The water boils at 100 degrees C. It evaporates and then condenses back down through a chamber, and we collect it as water. So the impure water, the salty water, is boiled or heated. And it's not just warmed up, it's heated until it evaporates. The evaporated water is then condensed. And what we do is we condense it back down to our liquid water. All the salt is left behind. The salt does not boil and is left behind. So we heat the salty water until it evaporates. The water is evaporated and then condensed, and the salt water or the salt in the water does not boil and is left behind. So we obtain potable water by distillation that way. Obtaining potable water from salty water is more expensive than obtaining potable water from groundwater. Explain why and refer to the processes used in both methods. Right, okay, so to do distillation, I'm just going to move back up again. To do this process, we have to heat the water until it evaporates. That's a lot of energy and a lot of money. So actually heating the water is more expensive than simply treating groundwater through filtration and sterilization via chlorine. And that's all we have to do really with groundwater. So to write this as a 2-marker, we would say heating the water in distillation uses a lot of energy and is expensive. Groundwater treatment only needs filtering and, well, sterilizing with chlorine. Only needs to be filtered and treated with chlorine. Okay, quite a lot there for 2 marks. Question 4. So we're pretty much 3/4 of the way through this test now. Industries use the Earth's natural copper resources to produce useful products. Figure 4 shows the world production of copper from 1900 to 2020. Describe the trend by the graph in figure 4. Now for 2 marks, I'll be honest with you, I actually struggled to see the second mark. I had to look this up because naturally your teachers tell you to talk about the trend in the graph and then use data from the graph to support your answer. Now what this was looking for is rate, talking about the change in the line of best fit. So let me just explain what I mean by that. So it says, describe the trend. Well, the trend is that it increased from 1900 to, 2024. So the production of copper increases from 1900 to 2024. But the second mark for this talks about the rate. At the start, the tangent isn't as steep as at the end. So the rate increased towards the end. It started off slower and the rate increased. So increased over time. So a tricky one there for 2 marks. It's not something that I particularly would have been led towards. I would have naturally used data to support my answer to get that second mark, but that's not what it was after. Suggest one reason for the trend in figure 4. Well, why has the production of copper gone up? Well, because we need it. It's like anything. Why did the production of cars go up? Well, we need more cars. There's more people. So the trend is linked to people. So increased population means an increased demand. Question 4.3, I think this is the last one on 4. Suggest one reason why the trend cannot be used to accurately predict the future of the production of copper. We don't know what the future holds, basically. We might run out of copper in 2 years. We don't know. There might be a sudden demand, a sudden surge for copper. And then we don't have any left after 2030. So we don't know. So it's a finite resource. I'll spell it correctly. It's a finite resource that could run out. We don't know what the future holds. Likewise, other answers might be we might have an increase in demand for it. So we might require more copper in the future, which requires us then to produce more. So you could link it to demand as well. High-grade copper resources are now difficult to find. We basically mine them all. So phytomining is used to extract copper from low-grade ores. There's 5 stages A to E in phytomining. The stages are not in the correct order, so it gives you the stages there. What's the correct order? Well, in phytomining, what we do is we plant plants in the ground, crops. They absorb through the roots all of the copper ions, and then we harvest the plants, burn them, and do a separation technique called electrolysis to get the copper out. So which one follows that description? Well, first of all, we're looking for something where we talk about planting plants. That's the first thing. Copper dissolved in ash, plants absorb metal compounds, plants are burned, plants are harvested, solution of copper compounds electrolyzed. Well, it doesn't really talk about the planting. So what's the next step? Well, the plants absorb the metal compounds. So we need one that starts with B. So it's got to be either this one or this one. We can get rid of these straight away. And that's what I would do in a in a multiple choice question. Then the next step, once it's absorbed, we need to harvest the plants. Plants are harvested, D. So it has to be this one. I could stop there if I wanted to, but let's check that the other bits match up. C, plants are burned, yep. A, we dissolve it in acid, correct, we need a solution. and then we extract it via electrolysis, E. Perfect. So the answer is the second one down. Here we says give 2 disadvantages of phytomining compared with traditional mining methods. Do not refer to costs. Well, phytomining, because you've got to plant the crops, takes up a large area. You have to have fields and fields of crops. It also takes a long time for those crops to grow. So you've got to wait for all that low-grade copper ore to be basically absorbed. And then the final thing is, well, when you do, it's all low grade, it's low yield. You don't get quite a lot of copper, not as much as you would through mining. So there's lots there. So I would say it's a slow process. And the second one I would say is low yield. So it takes a long time and we don't actually get a lot of copper at the end of it. Now, it's a good process when we run out of copper to get whatever remaining copper we have, but as an alternative to mining, it's not great. So 4.6 says in 1 year, 8.89 times 10 to the 9 kilograms of copper was produced. So that's how much copper was produced in 1 year. 41% of this copper was produced from recycling copper. The energy needed to produce 1 kilogram of copper ore is 70.4 megajoules, and the energy needed to produce 1 kilogram of recycled copper is 27.2 mJ. Calculate the difference in energy used if all the copper was produced from recycling. Give an answer to 3 significant figures. Right, so to do this one, and this is a 5 marker, quite a tricky question, probably one of the hardest questions on the paper. We first need to know how much in terms of mass of copper was produced from just recycling. Now we know that 8.89 times 10 to the 9 kilograms of copper is the total. So what's 41% of that? So that's what I'm going to work out. So I'm going to do 41 over 100 times 8.89 times 10 to the 9. That'll give me 40. That'll give me basically how much copper was recycled. So that's what I'm going to do. I'm going to type that in my calculator now. So massive number, and I'm going to write it all out for you. Rather than in standard form, I'll write it all out. 3,644,9 with 5 zeros. So that's how many, and it's a lot, kilograms was produced from recycling. So let's find out how much energy that took, okay? So it said for 1 kilogram, it was recycled copper. Let's have a look. It was 27.2. Now we've got way more than 1 kilogram. So we've got this value here multiplied by 27.2 mJ, and that will tell us how much energy it took to extract that copper. So the value in terms of energy was 9.91 times 10 to the 10. Okay, that's how much energy was used to get the recycled. Now we're going to do exactly the same. We're going to do it for the non-recycled, basically the copper we got from the ore. Now to do that, I know that the total is 8.89 times 10 to the 9. So I'm going to subtract the recycled copper, and that will leave me with the mined copper, the copper from the ore. So 8.89 times 10 to the 9 minus 36449. Let's see what that is. So this one is the ore. That's how many kilograms were just from the mined copper. And that took 70.4. So we're going to multiply that value by 70.4. 0.4 mJ, and that will tell us how much energy it was for just the copper ore. So now I've got the two energies, the energy for the recycled and the energy for the mined ore. I can find the difference in terms of energy. So we'll do 3.69 times 10 to the 11 minus 9.91 times 10 to the 10. .70 times 10 to the 11. That's how much energy was used. In terms of difference in energy, quite a lot to go through there. If you don't understand that, please pop it in the comments. I'm more than happy to sort of go through that maybe a little bit slower, answer any questions on where those numbers came from if needs be. Right, second to last question now. Atmospheric pollutants or pollution is emitted by cars. Some car emissions contain nitrogen dioxide. Describe how nitrogen dioxide is produced in the engine of a car that burns fossil fuels. Right, so nitrogen is basically an impurity that we have in fuel. When we put a petrol in our car, it will contain some nitrogen. And what happens is that under high temperature and pressure, that nitrogen impurity reacts with oxygen and makes NO2. So for three marks, under high temperature and pressure. Now, if you're ever being asked a question about car engines, this will always be 1 mark. So even if you don't understand how a combustion engine works and why would you need to, the answer is always going to be high temperature and pressure for one question like this. So under high temperature and pressure, the nitrogen in the fuel reacts with oxygen, and that comes from the air, if you need to know, as it's drawn in, reacts with oxygen to produce NO2. Okay, now we're given some data here, and I'm going to have to go over 2 pages like this, and it says, this table 3 shows the concentration of nitrogen dioxide in air in 3 different areas for 1 week. The mean value of nitrogen dioxide in the air for the whole week in the city centre is 33 micrograms per metre cubed. Calculate the value of X for the concentration of nitrogen dioxide in the air in the city centre on Sunday. I think this, for 2 marks, is an absolute pain of a question. Probably the second hardest question on the paper. One that takes way more time than 2 marks. And I think it's probably a bit of a pain for most people. But we'll work through it. I'll show you what happens. So the average was 33 micrograms per metre cubed per day. All right. For the whole week in the city centre is 33 micrograms per metre cubed. So if I know that, how many days in a week? 7. So we're going to do 33 multiplied by 7. Then we're going to subtract all of the city centre's values from it. Because then if I know what the average is per day for the whole week, I can start to subtract every day city centre value from it. Okay, so now we're going to subtract all of those. We're going to say 35, 37, 37, 34, 37 and 29. And the remainder will be X. So minus, and I'm going to put it in brackets here, 35, 37, another 37, a 34, a 37 again, a 29. And if I take all of those away from it, I will just have what's left for X. That's what I'm going to do now. So X is 22. Like you say, very quick when you do that, but to try and work it out, trying to understand what to do, to put it in your calculator, there's a lot to do there for 2 marks. And it says here, explain why there is uncertainty is more significant for the countryside data. Right. So each value in table 3 has an uncertainty of plus or minus 2 micrograms per meter cubed, meaning that the value reported in this table here could be 2 higher or 2 lower. So let's take Monday as an example. For the countryside, the actual value could be 10 or 6. And what they've done is they've quoted 8. Now, it could be 2 up, it could be 2 below, but why is that an issue or more significant for countryside data? Well, a change of 2 affects this number dramatically. And because using small numbers, it's more significant because any change, especially 2, is a big deal. So why is it more significant? Values for the countryside are smaller. Any change will be significant. So if you're looking at the table for the city centre, a plus or minus 2 of, well, let's take Monday's value for city centre, a plus or minus 2 for this wouldn't really affect it that much. You know, you're having highs of 37, lows of 33, you're pretty close to that value, and really it's not going to make that much of a difference. But for small numbers, a change of plus or minus 2 affects it dramatically. So nitrogen dioxide is removed from car emissions by catalytic converters. In a catalytic converter, nitrogen dioxide, NO2, reacts to produce nitrogen and oxygen. Complete the equation for the reaction. You should balance the equation. So it's given us our nitrogen dioxide and it says it produces nitrogen and oxygen. We make that and that. So they are our products. So we need to do nitrogen, which is N2. And remember, nitrogen and oxygen are diatomic molecules. They're gases and they exist as N2 and O2. So once you've worked that out, now it's just a case of balancing. So to balance the nitrogens, we need 2 on that side. So 2 times 1 is 2. So 2 nitrogens here, 2 nitrogens here. Now we need to balance our oxygens. So 2 times 2 is 4. So 4 oxygens on the left. So we need 2 here because 2 times 2 is 4 there. So it's 2NO2 goes to give N2 plus 2O2. Question 5.5 says the catalyst in a catalytic converter contains platinum. Platinum is a finite resource. What is meant by finite? Well, we covered this actually when we looked at copper, but it wasn't a question. Finite means it will run out. We will eventually run out of it. Question 5.6, it says emissions from cars contain carbon dioxide. Oh, sorry, just a quick message on 4.6. I'll finish this question, then I'll go back up to 4.6 and just explain it. So emissions from cars contain carbon dioxide. Explain why carbon dioxide emissions during use and operation are not the total carbon footprint of the car. Refer to stages of the life cycle assessment in your answer. So when you're using a car, it produces carbon dioxide, but that's not the total amount of carbon dioxide that car has produced in its lifetime. Actually, making the car in manufacturing, that took some carbon dioxide. It was in a factory, it was using machines. Also, to transport that car from, let's say, it could be China, it could be the US, importing them on big ships, that's going to take a lot of carbon or produce a lot of carbon dioxide too. So there's a lot more to it than just the production in the car. So we need to say manufacturing the car also produced CO2. And also, actually, what we haven't touched upon, what about getting rid of it? When people are fed up with the cars and want them crushed or changed and recycled, that's going to use produce some CO2 as well. So let's say getting rid of, and then also transportation. There you go. Right, we need to go back to 4.6 and just go over that in a little bit more detail, because if not mistaken, yeah, it was this really tricky question. Right, I'm just going to change colour slightly here, just so I can go over the other text. Right. So what it's saying is that this is the total. This is 100%. That's 100% of all the copper that was produced that year. And out of that, 41% of it was recycled copper. Okay? And that's that first bit here. I'm finding out the mass of recycled copper. So this many kilograms was produced. Okay? To do that, I did 41 over 100 to get my percentage, and then multiply by 8.89 the total to get my kilograms of recycled copper. Why did I do that? Well, I need to know the difference in energy used if all the copper that was produced was from recycling. So I need to know how much energy was used for recycling alone, how much energy was used to produce the mined copper, and the difference, that will be the difference in energy. Now I can't find out energy, I can't work this out, this value here, my energy value, unless I know how many kilograms I have. Because for each kilogram, it uses a certain amount of energy. So I need to know the kilograms of the copper ore, the kilograms of the recycled copper, and then I can work out the total energy for each. So the total energy used for the recycled copper was this value here, the recycled value, how much I got from recycling, times the 1 kilogram recycled copper, okay? And that's how much energy in megajoules it took to recycle my copper, or to get copper from recycled copper. Now, the second part here to the question is to work out what is the copper or energy used for the copper ore. So to find this value here in kilograms, what I did was I took the 8.89, the total copper, the 100%, and I subtracted the recycled copper out of it. And what was left was my kilograms of the ore. Okay? Now I know the mass of the copper just from the ore. I can multiply it by the value 70.4, because for every kilogram, that's how much energy was used, and I get 3.69 times 10 to the 11 mJ. So now I know the energy from the ore and the energy from the recycled. I can find the difference by subtracting effectively the bigger one from the smaller one, and I get 2.7 times 10 to the 11 mJ. Now, if that doesn't help, I'm terribly sorry. What might be a great idea is to perhaps, if you've got a teacher and you're watching from another school, then maybe go to your teacher, see if they can explain it a different way. But what I would suggest is maybe looking at this question in a different light tomorrow, getting it out again and see if you can work through it with a clear head. You know, because sometimes just giving it 2 minutes, 5 minutes, 24 hours actually really, really helps, because you come back to it with a fresh mind and think, actually, yeah, I can see how I got that number now, rather than just trying to frustrate yourself with understanding it now. But I'm more than happy to go through it again if we need to. Right, I think we've now got the final question, question 6. So it says ammonia is produced when a mixture of nitrogen and hydrogen reacts. And the equation for the reaction is, and it says there, nitrogen is obtained from the air. The mixture of nitrogen and hydrogen must not contain carbon dioxide and oxygen. Explain how the sample can be tested to show that carbon dioxide is not present in the mixture. Right, so really all it's asking you is what's the test for carbon dioxide? So if you tested this with lime water, if the lime water turns cloudy, you know you've got carbon dioxide. If it stays clear, then you know you're good. So really that's a long-winded way of asking what's the test for carbon dioxide basically. Then 6.2 says a catalyst is used in the reaction. Explain how a catalyst increases the rate. Catalyst does this in two definitions, if you like, or two statements, but it does this by finding an alternate pathway, finding another way for the reaction to occur. And by finding an easier way for this reaction to occur, it lowers the activation energy. And because it lowers the activation energy, it allows the reaction to happen quicker or at a faster rate. So for 2 marks, I would also write about it being unchanged. So I'll show you what I would write. The catalyst provides an alternative pathway and lowers the activation energy. Okay, this speeds up the rate of reaction, which it already is mentioned here. But at the end of the reaction, the catalyst remains unchanged. So a catalyst only provides an alternative pathway. It doesn't, in essence, get involved in the reaction. It doesn't change at all. If you start with it and the reactants, you'll get it at the end in the products. So 6.3 talks about this, the Haber process again, the reaction between nitrogen and hydrogen. And it says the reaction reaches equilibrium. Explain how equilibrium is reached. So this is a reversible reaction, okay? It can go both ways. And we only reach equilibrium, meaning the same amount in terms of rate on the right and the same amount in terms of rate on the left, equalizes when they're equal, when we have the same rate in the forward reaction as we do in the reverse. The rate of reaction in the forward direction is equal to the rate in the reverse direction. The rate of reaction in the forward direction is equal to the rate of reaction of the reverse. Now this only happens if it's in a closed system. Meaning nothing can get in or out, because if we let any products or reactants escape, especially when they're gases, then they won't be there to react. So we have to be in a closed system. The rate of the forward reaction, or the rate in the forward direction, is equal to the rate of the reverse. Now this is also the definition for dynamic equilibria. So if you want to write this on a flashcard, that might be useful. Suggest how the catalyst affects the equilibrium position. Give one reason for your answer. Well, it doesn't affect position. A catalyst speeds up reaction. And because this reaction happens in 2 directions, it will speed it up in the forward just as quickly as it will speed up the reverse. So it doesn't affect the position of equilibrium. So no effect on the position because it speeds up the rate in both directions. Now 6.5. What is the effect of increasing the pressure on the reaction to produce ammonia? Right, so this is to do with Le Chatelier's principle. And what Le Chatelier said is that whatever changing conditions you do, the system, the reaction, will oppose that change. So it will do the opposite. So for pressure, that's probably the hardest one out of all of the changes because you have to look in the terms of moles of gas. So how many gas molecules, and I might have to just quickly erase part of this here just to make it a bit clearer. So on the left side of this, you've got 1 mole here and 3 moles here. So in terms of molar ratios, you've got 4 moles of gas on the left. And on the right hand side, you've got 2. Okay? So if you increase pressure, Le Chatelier states that it will move to the side with the least moles of gas. Now that's the right side because it's got the smallest number, the smallest amount of gas. So if it's moving to the right, what will happen to ammonia? Well, we're moving to this side to make more of it. We're moving to the side it's on. So the yield of ammonia will increase. We will make more of it because it's moving to this side, because it's got less moles of gas. Final question says the forward reaction is exothermic. So in that reaction we just looked at, the forward reaction is exothermic. That means that the reverse reaction will be endothermic. Explain the effect of increasing the temperature on the yield of ammonia gas produced at equilibrium. Well, we need to know what exo and endo mean. Exo means to give out heat energy and it will start to feel hot. Okay? Endo means heat energy is taken in from the surroundings and it will feel cool. So if we start to increase the temperature, it's going to get hotter and the reaction will want to counteract that change by trying to cool down. So it will shift to the endothermic side, to the left. So let's go back up to our equation. Let's have a look. Well, if we shift to the left, to the endothermic side, we're going to move away from ammonia and we're going to produce less of it. The yield will decrease. We're going the wrong way. So for the final 2 marks, the yield of ammonia will decrease. And why will it decrease? Well, because the reaction will shift to the endothermic side. Right, guys, I hope you found that useful. Sorry if it was a little bit confusing at points. This is the first time doing this. I'm going to do another one next week, but do it on paper 1, so you've got both bases covered. And then if I get a lot of positive feedback from it, I can try to do some more years. So I could try and do maybe 2020, 2019, which was the pre-COVID year. But whatever you want me to do, I'm more than happy to sort of meet your needs on this one. But yeah, hope you enjoyed it, and yeah, speak to you soon.